Hi guys, welcome back to my video about programming in Go. This video is part 3 of my lecture series on concurrency in Golang. In this part, I will show you concurrent web crawlers as examples of concurrency. And then I will also discuss some other features with channels and Go routines, including unidirectional channel types and goroutine links. In the first two parts of concurrency, we have learned basics about goroutines and channels. Let's first review those basics. Goroutines are concurrent activities in a Go program. The main goroutine is the initial goroutine in a Go program that executes the main function. New goroutines are created by the Go statement, which are function calls prefixed with the keyword Go. The function call in a Go statement will be executed in the newly created Go routine, but its arguments are evaluated in the current Go routine. When the main Go routine exists, all other Go routines terminate abruptly. In the message passing styles of concurrent programming, Go routines communicate with each other via channels. To create an unbuffered channel, we call the built-in make function, passing the channel type as the only argument. To create a buffered channel, we add a positive capacity as the second argument of the function make. Fundamental operations on channels include send to a channel and receive from a channel. Another operation is to close the channel by calling the function close, passing the channel as the argument. Unbuffered channels are synchronous, meaning a send to an unbuffered channel blocks until there's a Go routine executing the receive from the same channel, and vice versa. In this video, I'll show you a practical example of concurrency using the message passing style. Our example is based on the web crawler exercise from a tour of Go. In this exercise, we are given a web crawler without concurrency. You can run it here. Run. The main function of this program simply calls the function crawl, passing a given starting URL and a depth of crawling, which is 4 in this example. So here it will crawl all of the pages starting from golang.org to the depth of 4. Function crawl also uses an instance of the fetcher interface, which represents a web of pages. The given program already implements the fetcher interface with the fake fetcher type and creates an instance of fake fetcher named fetcher that maps 4 URLs to 4 fake web pages. This instance of fake fetcher is passed to the function crawl in the main function. Now consider the web crawler given the tour of Go, focusing on the fetcher interface and the crawl function. The fetcher interface has only one method, fetch, which takes a URL as argument and returns the body of the page at the given URL and a slice of URLs found on that page along with an error. Function crawl uses an instance of the fetcher interface to recursively crawl pages starting with the given URL to the given maximum of depth. This implementation of function crawl is a depth first search algorithm. First, it explores the starting URL by calling method fetch of the fetcher. Then for each URL linked from the starting URL, it calls a function crawl again to crawl from that URL with one level lower in the depth. Our task is now to make those recursive calls to function crawl concurrent. Our first version of concurrent web crawler simply makes each recursive call to crawl be executed in a new Go routine by adding the keyword Go in front of the recursive call. Then the calls to crawl are executed concurrently. This version displays only one URL in the output. It starts all the Go routines, one per call to crawl, but it doesn't wait for them to finish because when the main Go routine terminates, all Go routines abruptly stop. There is no direct way to wait until a Go routine has finished, but we can change the inner Go routine to report its completion to the outer Go routine by sending an event on a shared channel. So in version 2 of concurrent web crawler, we modify function crawl, making each inner Go routine to report its completion. An inner Go routine is the one created in the body of the for loop that ranges over the slice of a URL found in the page at the starting URL. The inner Go routine reports its completion by sending number 0 to a shared channel CH, which is created as an unbuffered channel before the for loop. The send operation must be executed right after the completion of the call to crawl in the loop body. So we need to place both the function call crawl and the send to CH in the same Go routine. This is done by wrapping them inside a function and calling that function with the Go statement. Recall that a send to an unbuffered channel must be synchronized with a receive from the same channel but executed in another Go routine. Therefore, we make the outer Go routine, which starts the for loop, to receive all the events sent by the Go routines created in the for loop. The outer Go routine needs to receive all the events before returning to make sure all the Go routines are complete. Here we know the number of events is equal to the number of elements in the slice URLs. That's why we use the for loop that ranges over the slice URLs to receive all the events. Note that version 2 of concurrent web crawler still produces incorrect output because the single variable u is shared by all the anonymous functions and updated by the successive loop iterations. Recall that we cannot control when a goroutine starts. This means that the inner goroutines may not execute in the same order they are created. But the inner goroutines only read the value of u when they execute, not when they are created, because the value of u is used inside the body of the anonymous function. Therefore, by the time an inner goroutine starts executing the anonymous function, the for loop may have updated u and started another iteration or finished entirely. As a result, many of the inner goroutines may end up using the same value of u. For example, suppose the values of u that the for loop iterates through are URL1, URL2 through URLn. When u receives value URL1, the first inner goroutine is created but not executed, for example. And when u receives value URL3, the third inner goroutine is created and executes right away. And at that time, the first inner goroutine also starts executing. Then both the first and the third inner goroutine could use the same value URL3 of u. As a result, they fetch the same URL twice. In the version 3 of concurrent web crawler, we correct the error in version 2 by adding an explicit parameter w to the anonymous function definition. Then parameter w is passed to the recursive call to function crawl. The value of u updated by the loop iterations is then passed to the call to the anonymous function. Note that this argument u is evaluated by the outer goroutine before the inner goroutine is created. Parameter w holds that value of u when the inner goroutine is created, and it belongs to the inner goroutine only. That value of w is passed to the recursive call to crawl when the inner goroutine executes. This ensures that we use the value of u that is current when the recursive call to crawl is executed. Now this concurrent version produces the same result as the non-concurrent version. We have seen a practical example that uses both the send and receive operations on channels. Now let's discuss more on the closed operation of channels. Recall that a sender can close a channel to indicate that no more values will be sent. There's no direct way to test if a channel is closed, but you can use a receive expression that produces two results. The first result is the value received, And the second one is a bool value that is false if the channel is closed and drained. Being drained means there are no more values to receive from that channel. You can also use the range operation on a channel. If C is a channel, then the loop for I colon equal range C receives values from the channel C repeatedly until the channel C is closed. Note that channels are not like files. You don't usually need to close them. Closing is only necessary if the receiver must be told there are no more values coming, such as to terminate a range loop like this one. Here is an example that uses the range and close operations on a channel. This program has function Fibonacci and function main. Function Fibonacci takes an integer n and a channel C as arguments and computes the first n Fibonacci numbers, then sends them to channel C. We close the channel C after it has received all and Fibonacci numbers. In the main function, first we create a buffered channel B with capacity 10. Then we call function Fibonacci passing capacity of B and channel B as arguments. This will compute 10 Fibonacci numbers and send all of them to channel B. The call to Fibonacci is placed in a go statement, so it will be executed in a new go routine. Finally, we use a loop that ranges over channel B to display all numbers that channel B has received. Note that if we draw close C in the Fibonacci function, then the for loop in the main function would cause a deadlock because it keeps trying to receive values from channel B, but at some point, channel B has no more values. In all examples of channels we have seen so far, you can both send and receive on the channel. But channels supplied as function parameters are often intended to be used exclusively for sending or exclusively for receiving. For example, the channel parameter in the Fibonacci function was only used for sending. To document this intent and prevent misuse, the Go type system provides unidirectional channel types. The send only channel type is written chan left arrow followed by an element type. This channel type allows sends but not receives. Conversely, the receives only channel type allows receives but not sends. It is written starting with the left arrow, then the keyword chan followed by an element type. For example, consider function counter that takes a channel as argument and sends all integers between 0 and 99 to the channel argument. This channel argument is intended to be used exclusively for sending, so we declare it to be a send-only channel of int. As another example, consider function squarer that takes two channels as arguments. The first argument, out, is a send-only channel of int, and the second argument is a receive-only channel of int. This function receives all values from the receive only channel until it is closed by using a range loop. The square of each value received is then sent to the send only channel out. The channel out is closed after the loop. Closing a receive only channel causes a compile error. So if you close channel in function squarer, it will cause a compile error. Unidirectional channels can be used in a pipeline, which is a collection of goroutines connected together so that the output of one is the input to another. In this example, we have a pipeline of three goroutines that execute three function calls: counter, square, and a printer, respectively. The printer goroutine is the main goroutine. The other goroutine are new goroutines. The first goroutine, counter, generates integers from 0 to 99 and sends them over channel naturals to the second goroutine, squarer. The squarer goroutine receives its value squared and sends the result over channel squares to the third goroutine, printer. The printer goroutine receives the square values and print them. In this example, you also see that channels naturals and squares are bidirectional, but they can be passed to arguments that are unidirectional channel type. This allows a channel, such as squares in this case, to be used for both sending and receiving in a pipeline. In the last topic of this lecture, I'd like to discuss a common issue you may encounter with concurrent programming in Go. That is the issues of goroutine leak. Goroutine leak is a bug occurring when a goroutine is not terminated and left hanging in the background for the application's lifetime. Unlike garbage variables, leaked goroutines are not automatically collected. So it's important to make sure that goroutines terminate themselves when no longer needed. Note that just like garbage variables, leaked goroutines don't cause a runtime error, but they waste resources, especially in a realistic application. A common pattern resulting in goroutine leaks is the forgotten sender, as shown in the following example. This application make a parallel request to three mirrors, that is websites equivalent by geographically distributed servers. It sends responses over an unbuffered channel named responses, then receive and returns only the quickest response. Thus, mirror query function returns even before the two slower servers have responded. This resulting in a goroutine leak because the two slower goroutines would have gotten stuck trying to send their responses on a channel from which no goroutine will ever receive. The two slower goroutines would leak, trying to sent on a channel without corresponding receipt. So how to prevent goroutine leaks? For the forgotten sender pattern, a simple solution is to use buffered channels. For example, in the mirrored query application, we can change the responses channel to be a buffered channel with capacity at least 3, so that it can hold 3 responses in its queue. Each sender goroutine will stop right after it has sent the response. The quickest response will show up first in the queue and will be received and returned. The 2 slower responses will be discarded and there's no goroutine leak. That's all for this lecture. Thank you for watching, and I hope to see you again in the next lecture, which is also the last lecture about concurrency in Golang.